I really think it's fair to say we are staring down an astronomical engineering problem for us to, sustain a good quality of life on this planet. When we human beings today try to design materials, catalysts, drugs, when we try to work with chemistry, the analogy is that we are doing that with Stone Age tools today.
The problem is large, and it is something that should be at the forefront of pretty much everybody's minds. We're not going to be able to solve the problems of the future with the technology of today.
I've seen from the Department of Energy plots of what the U.S. energy needs would be if it wasn't for it's not just the computing, it's also the internet. All that data flowing through the pipelines, and every time they come to a switch, it all gets converted back into electronics and then back out. And so all this consumes a fair amount of power. No one bit costs much, but when you start multiplying that by very large numbers, it's a lot of energy.
The largest supercomputer today, for example, the one in operation in Oak Ridge Summit in the United States, that takes on the order around 14 megawatts. That's like, a small town could be powered by that. So that's just one big computer. And unfortunately, because of Moore's law, in order to get more computing output, people are going to have to be building larger and larger supercomputers, which is why it's predicted that our energy usage in computing, especially these data centers, will go from, in the low 10s or sub 10 to 20% by 2050.
The global warming is already happening. It's too late in that respect. What we need to work on is how to reduce CO2, which is already in the atmosphere. The way to do it is with carbon capture. We must accelerate science, accelerate the scientific discovery. And that we can do with technology. That's where quantum comes into play. That's where AI comes into play. Because we don't have time to spare,
Supercomputer and data center energy use, let's say, electricity use, is a pretty significant fraction of world energy use. So, the impact on the environment depends almost entirely on where that electricity comes from.
Growing up, of a child of the 80s, right? One of the things you always imagined was these giant Cray computers, right? And, they were massive and they always had funny shapes and, massive power plants to support them. But all that's evolved. Server farms today are things that we touch and we don't even know it. I mean, most of the consumer platforms now that we use and access on our laptop or even our phone, the data is partially stored somewhere in the cloud. And that cloud is, in essence, a massive horizontal supercomputer that can be configured both for processing, say, for example, images or AI activities around images, or actually just generally storing that data. So, to a large extent, even our banking data is at some level on an enterprise, supercomputer cloud server element. So we're touched by it every day and we probably don't even know it.
The first thing to do is to make a good distinction between supercomputers that are calculating things for scientists, basically, and data centers and server farms, which are running your social media and your business applications and whatever else. They are quite similar. If you looked at a photograph of them, they would look pretty similar. Racks of modules with CPUs and GPUs and memory and whatever else. They're both, building-sized machines. But if you look at the carbon footprint and the power consumption of these things, of course, it's dominated by the commercial business applications.
So in order to paint the picture, I'm just going to say, think about all of us and our daily lives with streaming movies, streaming video. What we're doing right now, we're conducting this interview over Zoom. Data is everywhere. And for AI, for some training algorithms, you need to really use terabytes of data, a huge quantity of data. When we're talking about AI, we're talking about training jobs that in the extreme case, can consume power that is the equivalent, if the origin of the power is from dirty origins like coal, is the equivalent carbon footprint of 5 cars through their lifetime. So this is obviously huge, and that's an extreme case, but this is all about the need to operate on these huge quantities of data and to train algorithms based on that.
We're just becoming an increasingly digitized society. I would also say the growth of artificial intelligence has drastically increased the need as well. So for example, if you use Google Mail, Gmail, when you're typing, it has this predictive type technology. All that kind of technology actually requires, even though it's very, very convenient, it also drives a lot of computer usage. So artificial intelligence is one of the main drivers of computing, which in terms is driving a lot of energy consumption. If you think about machine learning, there's the workload for training the model, but once your model is being used, it's called inference, then it's used all the time, right? It's been used by lots and lots of people. So the energy consumption of those AI models would just drastically increase by orders of magnitude.
The issue today is, even though a pretty big chunk of supercomputer time is spent on, let's say atomic simulations, so biochemistry simulations, chemical simulations, material simulations, a very large fraction of supercomputer time is spent on those, especially at the DOE supercomputers. Oftentimes, those calculations are not exact. So oftentimes those calculations, even though they're very useful and worth doing, they kind of have to be done in concert with laboratory experiments. Right? Or they kind of just give you qualitative information on the system that you're studying. And the hope with quantum computers is that you'll be able to increase the accuracy of those calculations eventually.
Even though data is everywhere and more businesses are using sort of data to inform their decisions, the core infrastructure, the core computing device hasn't changed a lot in over 50 years. They're still relying on the same binary sort of digital operations that they've always worked on. And that means that as our data becomes more and more complex, as for example, computing is being relied on for machine learning, and as the machine learning becomes more and more complex, meaning very, very complicated layers of neural networks, for example, classical computers really struggle to calculate using that data. And so that's where quantum computers come in being able to calculate and perform operations on much higher complexity, more difficult sources of data.
The computers that we have today are fundamentally limited in terms of their performance and what they can do. If we think about the caffeine molecule, it's got 95 electrons. If we were to try to simulate that with any given accuracy with the computers today, you would need, I think, 10 to the 48, or there's got a special number, it's like a quindecimal or something, but a ridiculous amount of memory that is equivalent to a tenth the size of the number of atoms in the Earth, which you could do, but would take a really, really long time or a lot of space. And actually a quantum computer could simulate that accurately with around 100 to 160 qubits. Regular computers that we have today aren't necessarily optimized or going to fundamentally be able to work and address those specific types of challenges, and many of those challenges tie really well into the topic we're talking about today of sustainability, particularly when it comes to thinking about materials discovery and optimizing for efficiency.
I think the sort of de facto standard use for a supercomputer is to simulate physics or chemistry, and that means fluid dynamics simulations. It means computational chemistry, calculating the properties of molecules. It's a long list of things, but it's basically trying to avoid having to do tons of experiments and tons of trial and error.
Supercomputers, artificial intelligence, all of these techniques that allow us to accelerate discovery, to do science faster. Say in the lab, I can work with some of the most talented lab chemists that I know. They can do maybe 5 experiments a week. They can build autonomous labs, and they may be able to do 100,000 experiments a week. But if you manage to build a computer model so that allows you to replicate some of the experiments in code, that maybe allows you to do 1 million experiments a week. So you can test out hypotheses faster. You can test out your ideas faster. All of those things allows you to answer questions so that you can eventually get to the breakthroughs that you need in order to solve some of these great issues, such as climate change.
Very smart mathematicians have found incredibly powerful, efficient techniques to simulate most of chemistry on a conventional supercomputer. And it's actually incredible how successful those methods like density functional theory have been in allowing you to accurately predict the properties of molecules without the need for a quantum computer. But there is still a whole bunch of problems where you have a particularly tricky molecule or a particularly tricky operating environment where these classical methods completely fall over. They give completely the wrong answer. Battery chemistry is a classic. So lithium-ion batteries have proliferated into every corner of our life. It's really unbelievable when you start reading into it how poorly people understand the chemistry of these lithium-ion batteries. I actually used to work on polymer lithium-ion batteries many years ago. I used to have my arms in a glove box mixing up chemicals, trying to find new lithium-ion batteries. And the state of the art is not really much more sophisticated than that, because people cannot simulate the chemistry that's happening in there.
The other examples that are quite often tied to are fertilizer solutions. When you create fertilizer, there's a nitrogen fixation process, and there's a specific molecule that exists in the grass outside, and for that process it does this nitrogen fixation process at room temperature or whatever temperature it is outside, and that's how Mother Nature operates. But with man-made fertilizers, we have to have incredibly high pressures, high temperatures in order to stimulate that same process to create the fertilizers that we have today, and that actually uses up around 2% of the world's energy, which is just completely mind-blowing. And it's like, for goodness sake, this is happening outside as we speak. But it's another example of where we just don't understand the world around us effectively, and where quantum computing can really help.
Well, I'm excited about quantum computing, right? Using nature to simulate nature. Molecules, atoms and molecules, they operate using the laws of quantum mechanics, or by the laws of quantum mechanics. Us here have different set of fundamental laws that allows us to kind of predict what we do, classical mechanics. And quantum mechanics and classical mechanics are very different. Current computers operate a lot on the laws of classical mechanics, classical information theory. Quantum computers operate on the laws of quantum mechanics. And so, if you build something that operates on the laws of quantum mechanics, it allows you to better, faster solve problems which are quantum mechanical in nature. We want to discover new molecules to capture carbon out of the atmosphere, right? So those molecules operate by the laws of quantum mechanics. So it's really good to use a quantum computer in order to simulate their properties, in order to calculate what they do. And so you can answer these questions, such as how much CO2 this molecule absorbs. You can answer these questions faster than you would be able to do with the classical computer.
The foundation of the world is quantum rather than classical. Classic computers are very inefficient when simulating the quantum world. These problems include drug molecular simulation, catalyst research and new material research. If we want to simulate the quantum world, we must have a computer that is different from classic computer.
We're essentially flailing around in the dark with a huge amount of trial and error. And that is, that's a pretty sad situation, especially given the scope of and the magnitude of the challenge that we face.
We are almost out of time to address climate change. There's all sorts of effects that climate change will have, not just on the environment, but on civilization, right? This is one of the major reasons that we care about it. There's things like droughts, more extreme weather events, crop failures, massive damage to infrastructure and property. These are only going to get worse, partly because CO2 emissions are cumulative. So the CO2 we put in the air now is still going to be there 100 years from now.
Human beings have made a catastrophic mess of our own planet, and we are now staring down the barrel of having to actively remove gigatons of CO2 from our atmosphere, right? It's not enough just to do your recycling and put a brick in the cistern. You're going to have to remove gigatons of CO2 from the atmosphere. And, I really think it's fair to say we are staring down an astronomical engineering problem for us to, sustain a good quality of life on this planet.
I think the use of quantum computers in climate change and looking at the future is probably something that we have to bring to bear. I mean, we have to bring all possible tools that we can to managing the climate. And the beauty about quantum computers is the fact that they can actually look at multiple streams of ideas in parallel, or multiple variables in parallel. And a lot of what we're dealing with climate change, relate to, whether it's, the CO2, whether it's, the temperature in the water, or how much CO2 can be absorbed in the water, or any aspects that we've contributed, such as coal production. These different variables are massively complex, and being able to bring a computer to bear on them that can look at multiple things in parallel is exactly what needs to happen. And that is probably one of the tools that we as humans need in order to move forward.
The other massive challenge for high-performance computing systems is the energy consumption required to process the data. I mean, what's actually alarming is that same energy consumption also applies to data centers. And I guess more and more people are using data centers to really crunch the numbers to train machine learning algorithms. And there's actually a really alarming statistic that actually machine learning is actually off limits to a lot of smaller companies, purely because of the costs required to power the computers that you need to perform machine learning. So it's actually inhibiting the uptake of machine learning, literally based on the kilowatt per hour energy consumption of these massive computational systems. And so, quantum computers have the ability to process data in new ways, much more simplified, more natural ways. And I really believe that that's also one way of allowing these huge energy consumption of data centers or sort of remote computational nodes to be greatly reduced. That opens up machine learning for much more wider applications, either on the move or sort of for cheaper type applications.
And so I think in 2019, it was an inflection point from the industry whereby we managed to do a calculation that could not be done classically within a reasonable amount of time. So this is the Google's Beyond Classical experiment, also known as the quantum supremacy experiment. And in that particular calculation, we benchmarked against the world's largest supercomputer, which is Oak Ridge Summit, and we found that the calculation of that was 1 billion times faster. Furthermore, from an energy perspective, we're talking about around 25 kilowatts for the quantum computer versus 14 megawatts for the supercomputer. So we're talking about 3 orders of magnitude. So in energy efficiency perspective, it is 1 trillion times more energy efficient for that particular calculation. And today's quantum computers too, if you have to realize that even the ones like superconducting quantum computers, they look very large, etc. And it turns out that there's actually orders of magnitude opportunity to reduce the cost, especially in the area of cooling. Mind you, the calculation that Google performed was not what we call a useful calculation that has wide industry applicability, but it kind of points to the opportunities, especially in the area of computation and energy efficiency.
From the macro perspective, imagine for a moment that you wanted to build a massively complex classical computer, like an exascale computer. Well, the Department of Energy ran a study a couple of years ago that showed that at certain sizes, you'd need to power it with a nuclear power plant the size of Fukushima. And obviously that's not a practical scenario. But the fact is, because quantum computers can scale exponentially, it gives you the opportunity to build incredibly powerful computers that could fit in the room that we're sitting in, and that would require a relatively small amount of electricity.
A lot of the things that we do on a computer are only approximate. So one of the biggest problems in the quantum computing area is we do not know what approximate algorithms on a quantum computer will be better than the current approximate algorithms on a classical computer. And to do that, you really actually have to have access to all the hardware, which we don't have.
If you start to think about a number of different things that we need to do to achieve quantum computing that's useful, like it can start to solve some of the problems that we're here talking about today, there are a number of things we need. We need bigger systems, so we need to be able to scale them. We need to have high quality qubits across this full scale of the system. So in tech terms, that's high coherence, high fidelity, and low error rates. So that's the scale, quality, and we also need to be able to build the infrastructure to control all of those qubits. Now, actually achieving all of those 3 things in tandem together is currently quite challenging, but the industry is making fantastic progress, and we're currently at this kind of turning point that's really exciting, whereby we're entering into what's sometimes known as the NISQ era, but basically it's early quantum computation with early applications.
然而，量子计算机目前面临着巨大的挑战。首先，在技术方面，我们人类开始去尝试去操纵微观体系下的电子、原子、光子这样的粒子。我们需要解决非常多的物理原理性的问题和工程实现的这样一些问题。这些粒子如何高效地相互作用起来？如何保证系统的量子相干性？如何提升每一步计算的准确度？如何去克服环境和系统本身的一些噪声？这些问题都需要我们不断的努力去探索和克服。
What quantum computers needs to do is to scale up to much larger qubits, much higher connectivity, much better interfacing with high-performance computing systems.
The first thing that you have to do is figure out a model that is based on leverage. My cell phone here, there's 1 billion transistors, right? And the semiconductor industry has invested $1 trillion over 50 years to be able to build those transistors with absolutely mind-bending reliability, process control, uniformity, you name it. If we could build qubits and if we could build the quantum computer in those same manufacturing processes, 1 million should not be such a big, scary number. I mean, it's like way less than what's in my cell phone here.
Where we are today in our industry is that I think we can show demonstrations, bits of what could be practical and which are kind of promising for, if we're able to scale, to get to the point where we're actually useful at, say, a large enterprise level. The question is whether or not the solutions that people are coming forward with on a demonstration level basis have the potential to scale to the complexity of the actual problem.
To be successful, quantum computers will one day look really boring. They'll one day look like, you know, normal computing devices, like boring black boxes that sit inside a rack, inside a big server room that no one cares about, no one has to maintain or worry about. No one understands that they're quantum objects because they're just there doing the job of processing data.
I hope that sustainability is at the forefront of pretty much everybody's mind, no matter what industry or what sector you're working in. And we see that with the UK government and the initiatives around, you know, more broadly from governments with sustainability development goals. And the UK, of course, hosting COP26 in November, which is very exciting. And quantum is no exception. At Oxford Quantum Circuits, we work with superconducting technology. So that means that we have cryostats to cool our quantum devices down to temperatures that's colder than space. Believe it or not, that takes power, and it takes quite a lot of power. These are problems that are going to be more specific to the R&D, to the development process. And there are a number of things and a number of ways that we can start to think about how we address that.
This is actually an area that, especially the supply chain, can definitely work on. There could be up to 5 orders of magnitude decrease in cost in terms of energy consumption for the quantum computers today. Today, for our quantum computers, with like a 50-ish qubits, it's already taking 25 kilowatts. And we believe that if we're going to be building these error-corrected quantum computers, you're going to need on the order of 1 million physical qubits. That kind of energy consumption is even bigger than what today's supercomputers are doing as well. So we're going to have that drastic improvement in the efficiency of the cooling of these systems, because if we were to build useful quantum computers, there is the potential that these useful quantum computers will take even more energy than the world's largest supercomputers today. So this is something definitely that we're looking into, and we'd love the industry to work on it together.
What's exciting is that quantum computing is evolving at a time that we are aware of sustainability. And that's the exciting point, is because we can actually make these decisions now. And so some of the things that we've done at Oxford Instruments is, you know, as we scale up the refrigeration, the cooling, the dilution units for quantum computers, we're making them, in essence, expandable or recyclable. So our larger fridge that we're working on today can actually be expanded and connected together with additional units so that it expands and grows. The other thing that's exciting is that we've now brought into what we call the secondary insert into the process, which really allows a customer to make their quantum computer future-proof by being able to reuse that insert as they grow and scale their platform, which is very exciting.
I think you have to remain hopeful. As an entrepreneur, you have that, you know, can-do-if attitude and approach, and you know, we are absolutely determined to make sure that the technology we're building from a quantum computing perspective will have that positive impact. So more broadly than quantum technology, we're seeing so much incredible innovation, and the minds of today are really tuned into this stuff, way more than we've seen in previous generations. So I have hope based on the tech, based on the people, based on the evolving culture and mindset.
I think ultimately this technology will give us more than it takes. If you believe that the way forward is through technology and wise use of technology, I think it's like being in 1950 and looking at 50, 60 years out and trying to figure out what 3 things should you have done. Nobody could see the internet. Nobody could see e-commerce. Nobody could see Google. So I think we will not know the true impact of this technology, probably only beginning to realize it in the next 15 to 20 years.
People aren't just looking to governments now, they're looking to science. It's the role of science, it's the role of innovation and technology to help deliver for the good of society, to work more closely with government, and to help find the opportunity in the midst of challenge.